So quantum mechanics is the subject of the discussion here tonight. And look, it's the year 2014, and the first glimmers of quantum mechanics really came on the scene in the early part of the 20th century. Certainly by 1930 or so, the basic framework of quantum mechanics was in place. And yet today, right, some 80 years later, there are still questions that are ripe for discussion at the foundation of the subject, questions that are still controversial. And we're going to discuss one of those controversial questions here tonight, so you'll see various perspectives on that. At the same time, quantum mechanics, of all the subjects of modern physics, has really been embraced by the culture. At least the language of quantum mechanics has been embraced by the culture. I mean, just to give a couple examples, right? So from Hollywood, right? We have quantum thrillers, right? We also have, quantum sporting goods, right? Golf clubs, quantum bowling balls, quantum baseball. We've got quantum cartoons, right? Oh, Alice, you're the one for me. But Bob, in a quantum world, how can we be sure? And then we have physicists talking dirty, right? I'd like to cover you in quantum foam, and you finish. I'm not going to. It's a family program here, right? So we also have quantum health care, right? So this one, quantum herbal canker sore gel. Nothing to do with the previous cartoon, completely separate. We have the quantum pendant, protects the body against any harmful rays. I like this one. We got the quantum vet, right? Use your cell phone to instantly diagnose and medically treat your pet at home. And I love this tagline over here. You see it at the bottom. Don't take me to the vet, use quantum vet. Which makes use of that famous of all adages, which is a surefire way to get words to rhyme is to use the same word. Now this one is absolutely my favorite. The quantum sleeper. Protection from biochemical terrorist attack, kidnappers, stalkers, bulletproof. And look at the loving couple over there about to enter the sarcophagus over there, right? So quantum mechanics in this sense is certainly out there in the world, but of course this is just the word quantum. This is really quantum bullshit, right? So what we're going to talk about here tonight is the real quantum mechanics. And what I'm going to do here for just about 10, 12 minutes is run through the basic ideas of quantum mechanics. Again, I think that's probably familiar to many of you, but just to make sure that we're all on the same page, and that will naturally lead us in to the issue for tonight's discussion, which is this quantum measurement problem. Okay, so for the basic primer on quantum mechanics, the key experiment that really gets the ideas of quantum mechanics across is the double-slit experiment. And I don't know, did any of you go to Spooky Action last year, just by any chance? Yeah, so a handful of you. So you may recall that we actually did the double-slit experiment on the stage last year. We're not going to do it again this year. We don't have enough time, but rather animations will give you the essential ideas. And if anyone doesn't believe the animations, just ask someone whose hand was up, because they saw the real experiment done last year. Okay, so what is a double-slit experiment? The idea is this. Imagine that I have a gun that's firing ordinary pellets, like BBs, at a barrier that has two openings. Now, you'd expect that those BBs that go through the left slit will land aligned in a band on the left. Those pellets that go through the right opening will land in a band aligned with it on the right. And indeed, were you to do this experiment, that is the result that you would find. Now, what we're going to do is imagine dialing down the size of those pellets, those BBs, making them smaller and smaller until they are the size of little tiny particles. Let's just call them electrons. Imagine we're doing this with electrons. Well, you'd expect that if you run the same experiment, again, those electrons that pass through the left opening will land in a band aligned with the opening on the left, and similarly for those that pass through the right. That is what you would expect should happen. And I think as many of you are familiar, this is not what happens when you do this experiment. Instead, if you do this experiment, you get results that look rather different. They look like this. You get a bright band next to a dark region, next to a bright region, next to a dark region, next to a bright region, and so forth. And that data, that strange data, is really what impels us toward quantum mechanics. Now, that data is strange because it's not what we would think should happen. We expect to get 2 bands, and we get more. But it turns out that that pattern, bright, dark, is a familiar pattern to most physicists. I mean, we are trained from birth to recognize that pattern, right? If you were to go to any physicist, 3 o'clock in the morning, shake that physicist, wake them up, and tell them, I got this data, bright band, dark band, bright band, dark band. The very first thing that they would say to you is, what the hell are you doing in my room at 3 o'clock in the morning? But after that, they would say, I know what that is. That's an interference pattern. That is the hallmark signature that there's some kind of wave phenomenon, taking place. Right? To understand that, let me just give you a little visual here where we're looking at water waves. Imagine I throw 2 pebbles. The first one over here makes these circular ripples, and I'll throw in a second one, and look what happens. When the waves overlap, in some regions they work together, but in other regions the peak of one wave is crossing the trough of another, causing the wave to cancel out, and those are those dark regions that you see on the screen. So this is exactly the kind of data that we're encountering. And to make that point a little bit more clearly, let me just show you an animation, same idea. Imagine you've got water waves going toward the barrier with the 2 openings. And again, regions where the waves work together, the water's very agitated. Regions in between where the peak of one wave crosses the trough of the other, they cancel each other out. And if on the back screen, I put bright regions associated with very agitated water, dark regions with not agitated water, look what I get. Bright, dark, bright, dark, bright, dark. And again, just to remember, that is the data that we find in this experiment. So this suggests that there is some deep connection between these particles, these electrons, and this other idea, a completely separate idea of waves. Now, at first sight, that might not actually seem all that surprising, right? Because water has water waves, but we all know that water is itself made of little particles, molecules, H2O molecules. So certainly we know that if a large collection of molecules behaves in a choreographed manner, those particles can yield a wave. So maybe what's going on in the experiment is just that. You've got a lot of electrons, and maybe they are behaving in a choreographed manner, and that way yielding a wave just like H2O molecules yield a water wave. Now, how would you test that idea? Well, you can run this very experiment, but only firing particle by single particle at this barrier with the 2 openings, and recording dot by single dot where each of those single particles lands on the detector screen. So let's run that version of the experiment and see what happens. So again, particle by single particle, we're recording on the back screen the history of all the landing locations, and this is what happens in this experiment. Dot by single dot, we build up the same pattern, the same interference pattern, the same data that suggests to us that there must be some kind of wave-like phenomenon involved to yield this interference pattern. So this is where things get really strange. Particles, electrons, little tiny dot, that is the image that we always have in mind. Waves are these spread out entities. How could a dot particle and a spread out wave somehow be connected? And this was the puzzle that physicists faced in the early decades of the 20th century, and many tried to figure out what could the connection between a particle and a wave be. And the natural suggestion that you might throw out is, maybe particles somehow are kind of smeared out in some way. They're kind of spread out in a way that we didn't realize. That idea, though, doesn't really work, because whenever you measure an electron, you find all of it. And if it was truly smeared out, you'd find a piece of it here and a piece of it there. And the idea that ultimately was settled upon, it came from the mind of a physicist, Max Born, was that the way to think about the wave associated with a particle is this. This is the new idea. The wave is a wave of probability. The wave is telling us the likelihood, the probability that the particle is at one location or another. So to show you a little visual of that, imagine this is the wave associated with a particle like an electron. Where the wave is big, that's a likely location to find the particle. Where the wave is small, an unlikely location. And where the wave is absolutely zero, that is a place where you simply will not find the electron at all. That's the picture that comes forward. Now, how would you test this idea to see if it's actually describing in reality how the world works? Well, the first thing is you need some kind of mathematical equation that allows you to understand how this wave evolves, how it changes over time. And that equation came to us from Erwin Schrödinger. Whether you understand the mathematical symbols or not, it doesn't matter, but it's good to see that there is a bona fide, rigorous mathematical equation behind all of the imagery that you will be seeing here tonight. That is the equation that describes how this wave, this probability wave, evolves over time. That's step one. So now you understand how things change in time. But to test it, well, you say to yourself this. Look, if at a given moment in time I've got this probability profile for where a particle should be located, the way I test it is I run the experiment of searching for the particle over and over again in identically prepared situations, and I count up the number of times I find it in one location or another. And if the theory is correct, you should find the particle more often where the wave is big and less often where the wave is small. So we can run that little experiment right here. So this is a simplified probability wave, the blue curve, and each of the x's is the result of an experiment looking for the location of a particle. And you see over many, many, many runs of the experiment where you record all of the locations where you find the particle, over time, they fill out exactly the probability profile that comes from the mathematical equation. And that agreement between experiment and theory is what gives us confidence that these ideas are actually describing how the world works. So just to kind of close the loop on this, going back to the double-slit experiment, how we describe it, well, in this new language, the electron should be thought of as a probability wave which hits the barrier with the two openings, and much like a water wave, when the wave goes through, it interferes, creates this pattern of locations where the wave is big or where the wave is small, and those locations dictate the likelihood or not of an electron landing in one of those regions. So now if we run the experiment with the little particles going out, dot by single dot, they are going to fill out that probability profile. Where the wave is big, there are going to be many electrons landing. Where the wave is small, very few. And where the wave was zero, the dark locations, no locations will be occupied by an electron at all. So this is the basic reason why we believe that these ideas are correct. So what this means is, by year 1930 or so, these individuals, the pioneers of quantum mechanics and others as well, we have over here Max Planck, we have Albert Einstein, Niels Bohr, Werner Heisenberg, Robin Williams, Erwin Schrödinger kind of looks like Robin Williams there. So these fellas here developed this structure which seems very odd, but able to describe the data. Okay, so that's the good part of the story. Now for the question that will occupy us here tonight, which is this. When we talk about, say, the motion of a particle like an electron, we describe it in this wave-like manner. It could be at one location or another still. But when we actually measure the electron, we find it at one single location. When we find it at one single location, we know where it is, which suggests that it must be the case that the probability wave has now spiked at that location because we know where the electron is. The problem is this notion of the active measurement affecting the probability wave in that manner does not agree with the mathematical equation. So we'll talk about this in more detail in just a moment. In fact, when you look at the mathematics, or in fact, when you think it through, even just recognizing that when we make an observation, we use a piece of equipment, that piece of equipment is itself made up of the very same particles, electrons and protons and neutrons, the same particles that we use the quantum language to describe. And therefore, if we have a situation, say, where the probability wave for an electron has some non-trivial value in one location and some non-trivial value in another location, and we go to measure the position of that particle, well, the measuring equipment should be sensitive to those two components of the probability wave, and therefore, in some sense, should register both of those outcomes at the same time. And that is something that never happens. We never look at a measuring device and somehow it is confused in giving us information about the location of a particle. That is the quantum measurement problem. How do we go from the spread out probability wave, which tells us a particle can be here or there or here or there, to the single definite reality that we all experience? How do we navigate from the place of probability to the place of definite reality? That is the question. And thankfully, we have some of the world's experts joining us here tonight to describe various possible solutions to that puzzle. So, without further ado, I'd like to bring them onto the stage. All right, our first participant, a philosopher at Columbia University, renowned for his insights into philosophical questions about time and space, modern physics, author of Quantum Mechanics and Experience, Time and Chance, and soon, After Physics will be released this fall. Please welcome David Albert. Also joining us, a mathematician, physicist, and philosopher at Rutgers University, studies the foundations of quantum theory, probability theory, and statistical mechanics, co-author of Quantum Physics Without Quantum Philosophy. Please welcome Sheldon Goldstein. Our third participant, theoretical physicist at the California Institute of Technology, and author of the award-winning The Particle at the End of the Universe. His research covers cosmology, field theory, dark energy, particle physics, and gravitation, just about everything else on planet Earth. Please welcome my friend Sean Carroll. All right, our final participant, mathematician at Royal Holloway University of London, a leading proponent, along with Chris Fuchs, of a new view of quantum mechanics known as Qbism. Please welcome the man with the coolest name in the history of physics, Ruediger Schack. All right, let's jump in. I'm going to arrange the evening in 3 chapters. And chapter 1, as we see here, we're going to discuss the quantum algorithm and its discontents. All right, so just to get us going, I want us to cast our mind back to the early years of the 20th century. Look at what we've done, right? We had classical mechanics. We could describe the motion of planets. We could describe the motion of objects around us. We had Maxwell's equations, we understood electricity and magnetism. And all of a sudden, the experiments that I was talking about just a minute ago kind of ripped all that out from under us, and we had this new quantum perspective that came online. So Sean, just imagine you were back there, right? And you'd love this classical world that had come down to us from the greats of Newton and Maxwell. What would it have been like to try to take on board these new ideas?
I think that the fact that we came to invent and accept quantum mechanics as quickly as we did, where this is the very royal we, including people in the past, is one of the most impressive intellectual accomplishments in the entire history of the human race, because every idea that was part of quantum mechanics just seemed to violate some cherished notion that we had really clung to. You know, we had this paradigm handed down by Galileo and Newton and their friends, and that was how physics was done, and it was a matter of which version of that physics we should accept. And quantum mechanics comes along and just changes all of the rules. So it must have been a combination of incredibly exciting and more than a little dizzying, and people must have been pinching themselves a little bit and like wondering, have we gone terribly wrong in thinking about this?
Yep. So I think all of us have heard that Einstein had his various tensions with quantum mechanics. Ruediger, where does that come from? Why did Einstein have this ultimate dislike for quantum theory?
Einstein had a notion of physical reality that clashed with the ideas of quantum mechanics, just as Sean just mentioned. And quantum mechanics has some strange features. If you think of quantum states as real, as describing reality, and you have situations where taking an action here, or let's say, make it more dramatic, take an action as far away as on a spaceship near Sirius, appears to have an immediate, instantaneous effect on my system here if the state of these two systems is entangled. Now, and that clashed with Einstein's sense of reality and Einstein's sense of locality.
Now, I think you raised that issue because later in the evening, you're going to give us your solution to that particular problem, which is a good one. We're going to come to that in due course. Let's build up to it step by step. So David and Shelley, you know, when I took quantum mechanics, it was the 1980s, and I think probably we're all roughly within 10 years of each other. So we all were taking it after the kind of dust of the revolution had settled. And I took it from a fellow who ultimately won the Nobel Prize, Norman Ramsey, great physicist, great teacher. And here's what he taught me, right? So if we can just bring up the approach to quantum mechanics that I was taught. So we were told that we had the input of how things are right now. And the idea was that we then were to make use of this equation that I mentioned before, this Ruediger equation. And using that, we would be able to predict the probability of what things, there weren't actually all those fireworks, but the probability of how things will be in the future. And for those who like a little bit of the equations, again, it does not matter at all if you don't follow the equations, but it's kind of good to see them. You start with a probability wave, or more precisely, a wave function at some initial time. You stick it into this equation, and then you get this output equation, which is the probability for how things will be later. This is what I was taught. I studied it hard, right? I did well on all the exams. Is this it? Is there some problem with this way of thinking about things?
You want to, I mean, I can start. It's what you want to know, I think typically in science, is when you see behaviors that are aptly summarized by equations like this, the natural thing to do is to ask yourself a question of the form, what would the world have to be like, or what could the world be like, such that a procedure like this correctly predicts what you're going to see. The business you're usually about in doing science is asking about how the world is. There are various kinds of ways in which the world can confront you, such as to raise questions like that. And what happened in quantum mechanics, as you say, is that we had this algorithm that was enormously successful in predicting how experiments were going to come out, but the algorithm didn't seem, at first glance, to readily lend itself to some kind of story about how the world needed to be such that an algorithm like this was going to be successful.
Right. So actually, I was just alerted, there's a question along these lines. Let me just quickly get it in here from Sam G from Twitter. Says that, you know, if there is an issue here along the lines of what you're suggesting, we're going to make that issue even more explicit as we go forward. Why are students taught this and not taught the actual issue itself? Is it expedience? Is it you need to learn it first this way and then later on, once you grasp it, the problems can...
Well, perhaps maybe the physics teachers want the students to have the same bewildering experience they did.
So let's make that bewilderment even a little bit more clear. So I was mentioning before the quantum measurement problem. Shelley, how would you describe the measurement problem?
Well, I guess your graphics before with the two-slit experiment did a really good job. I mean, you had the wave. You have an equation for the wave. You call it a probability wave, but if it really were a probability wave, it should be for the probability of something, and there might, if it's a probability for the position of the particle, there should be a particle with a position. So let's not take the word probability wave too seriously. Let's just call it we have a wave. But if we have just a wave, and this wave is going through both slits, then this wave is spread out. It develops an interference pattern, but it's still spread out. So why does anything dot-like appear at the screen? That's where the act of observation, of measurement, has to play a special role of causing that wave, that fundamental equation to break down and the wave to collapse. I think what Einstein regarded as the real problem with quantum mechanics, what he was so dissatisfied with, was that the observer seemed to play a fundamental role. Observers are, after all, just made of the same stuff everything else is made of. Why should there be different laws which have to be invoked to deal with the observer? That was really what bothered Einstein.
Right. So the idea is you got this spread out wave, and thereby, in some sense, the particle could be many locations, but yet when it's measured, you find it in one definite spot. How?
Well, and as you said, Brian, earlier during the introduction, if you were to treat the measuring apparatus straightforwardly in exactly the same way as you treat the particle, it's perfectly clear what these algorithms predict. You had the particle in a superposition. I don't know if we used that word or not.
Not yet, but we can use it.
In a superposition of being here and here.
A combination of being here and there.
Some kind of combination or some kind of situation in which it's neither here nor there, nor in both places, nor in neither place, but something else involving these two locations. And if you straightforwardly apply these equations, if you treat the measuring apparatus as just an assemblage of such particles, which is the way we've always treated such objects in the history of science, you're going to very straightforwardly get a result, and it was people like Schrodinger and von Neumann who first showed this very rigorously. You're going to get the result of the measuring device being in a superposition of having registered the particle being here and having registered the particle being there. And the same would apply, for example, to the brain of a conscious observer who looks at the measuring device.
Let me show you a little visual that we have just to emphasize that point, the quantum measurement problem. So exactly along the lines of what you're describing. Imagine I have a tabletop model of Manhattan, right? And I have a particle whose wave function, whose probability of being at any given location is described by that curve, right? Then I bring in a measuring device, this guy over here, and it measures that particle's position, and let's say it finds it at the Belvedere Castle, right? For those of you who are out of town, 79th Street Central Park, very nice place to visit, but that's a whole different story. Okay, so that is measurement number one. Let's now imagine that we have a probability wave that looks like this, and we perform a measurement as well in exactly the same manner. So we bring in our measuring device, and the measuring device shows that that particle is located now at Union Square, 14th Street. Good, okay. Now to the situation that you're talking about. Let's imagine that we have a combination of these two, a superposition, a combination of these two situations, where this is what the probability wave looks like. We bring in our measuring device, and as you were saying, since it's made of atoms and particles, it should be sensitive to those two locations, and therefore the output should be, something like that, right? A mixture of these two possibilities. But whenever we actually perform a measurement like this, we never see that happen with our devices. Our brains seem never to be cognizant of that kind of confusion, and that is the issue that we want to resolve.
And maybe it's worth saying that we do sometimes do these measurements in situations where we're confident that before we did the measurement, the wave function really did look like this two-peaked thing.
Yes, so we can really, in a sense, set up exactly what we're talking about over here. All right, so I think my understanding is there are probably 3 of us on the stage who are sympathetic to this issue, right? So, David, you think this is an issue. Shelley, you think this is an issue.
Yes. And
oh, that's what the philosophy is. You never get like just a yes, you got to like qualify it. Yeah.
I do think it's an issue, but I think it's an issue for odd historical reasons.
We will come to that. Yes, absolutely. Good. Sean, issue?
I think it's an issue that we can solve.
Yeah, okay, good. And now, Ruediger, you think it may even be a non-issue at some level, or just that you can solve it too?
Well, I would regard it as an issue that originally didn't exist, but then sort of the quantum mechanics was interpreted in a way that created the issue.
Okay, so it's an interpretational question that needs to be just rejiggered in the way we think about quantum mechanics.
Well, it's an issue that wasn't there originally, but
that has cropped up,
really
and you're going to disabuse us of all the silly thoughts that have led us to think that this is an issue in due course. Got it. Okay, good. All right, so what I want to do now is move into the possible solutions to this issue, at least for those who think that there is. So, when it's perhaps worth saying, when we talk about quantum mechanics, there is sort of one founding father figure who really thought that he had sorted this all out, and this is this guy here, Niels Bohr. So when you talk about it being a non-issue, are you kind of aligning yourself with Niels Bohr's position in that there basically needs to be a clear separation between the quantum description and the observer needs to be part of that story? Is that part of what you're going to tell us?
I certainly agree with Bohr that the observer, or let's say the subject, needs to be part of the story. But, Bohr is difficult to pin down in what he actually said and meant, and certainly some aspects of Bohr's thinking would not be, I would not be...
Good, okay, and you're going to tell us about that in just a moment. All right, so let's set up the issue, and I think a useful way of doing it is to have a kind of concrete example in mind, and the example I'm going to give you is just a very simple thing of a dart being thrown at a dartboard. And we're going to revisit that example in each of the proposed solutions as we go forward, not because the visualization that we're going to give you is spot-on accurate. For that, you really need the mathematical formalism. But I think it's good to have just a mental mnemonic of the ideas just to try to keep them straight. So the example that I'm going to use, if I have my handy dart here. Yeah, actually, can we bring the IMAG up for this guy, if you would, just so people can see what it is that I'm talking about. Yeah, good. Yeah, bring it up here. Can you get that? Good. All right, so I'm going to take this guy, right? I'm going to throw this guy, right? And there he goes. So classically, right, so that is what Isaac Newton says would happen, right? You simply throw the dart.
God, you're good.
Good, right? Yeah, right. Bullseye every time.
He has help.
Right. So that's what Isaac Newton would say. That's what our intuition says. The dart simply flies through space and hits the dartboard. Okay. Now, the approach to quantum mechanics that came down to us from Niels Bohr and the approach that I was describing in the early part of my remarks describes this in a somewhat different way. So if we can go to the standard quantum mechanical version. So here's the dart. It turns into this probability wave. The wave spikes, collapses at the location where the dart lands, and that is the description in the very standard Copenhagen approach to quantum mechanics. So I think we can run this guy a second time just so we have this one in mind. And the issue that we have is this notion of the wave spiking, the wave collapsing There's no equation that Bohr gives us to this, and therefore this is something that we don't really understand as a mathematical formalism. We want to go further and have something that really relies on a quantitative description of what's going on. So the first approach that we are going to take a look at, Shelley, you have been charged with being the defender, if you will, of this first approach, the de Broglie-Bohm approach. So in fact, why don't we just give a little bit of historical context first. There we got de Broglie up there, and then the other culprit responsible for this, David Bohm. Take us through, if you will, their way of thinking about what's going on in this situation.
Okay. I would say their way of thinking about it pretty much conforms to the way many people in the audience probably understood what you were saying in connection with the two-slit experiment. What did you see happen in the two-slit experiment? You saw particles going out from the gun one at a time, and definitely saw dots arriving at the screen, appearing on the screen one at a time. An interference pattern develops. You have the strongest, very strong evidence that there's a wave. Schrodinger quickly found an equation for that wave, and that equation predicts all kinds of other stuff. So we had good reason to be extremely confident that one element of quantum mechanics was that wave. You also would have thought you had good reason to think that as part of the one element of the system, this one particle system, is the particle itself. You're talking about a system consisting of a particle, there should be a particle, where particle means something with a position. So in addition to the wave, according to the Bohmian point of view, or de Broglie's point of view, you have an actual particle which has a position. And the wave is not so much fundamentally a probability wave, but what has often been called the guiding wave. The wave is relevant to the motion of the particle in a very precise way. So that in addition to Schrodinger's equation, you have another equation, an evolution equation for the particle, or for particles if there's more than one. This second equation, which is not standard, is something which is so sort of obvious that you could ask your good students to guess it. And almost any way of guessing which is remotely sensible would lead to the same answer. When you analyze that theory, which has a wave together with particle or particles, you find to your surprise, and it really is a surprise, that it yields all of the standard predictions of quantum mechanics probabilities and all, despite the fact that there's nothing random in the motion of this system.
So just to understand, so you got particles and waves, as opposed to the traditional description is you got a wave until you look and then it becomes a particle. In this picture, the wave is actually pushing on the particle, and that's what describes its ultimate motion.
You always got wave, you've always got particle, and it turns out after analysis that the wave turns out to function as a probability wave. It actually correctly describes the probabilities with which you'll find the particle in various places. And you also find out, almost paradoxically, that when you think about what you even mean by the wave for that particle when it interacts with the measuring device, with the screen, you find that this thing really does collapse according to the usual rules.
Yep. So we have a little visual again, just the mental mnemonic for this one. So if we go back to the dart in this case, in your version, the dart is always there. The wave pushes on it, and that governs where it lands. So we can just see that one again. Again, it's wave and particle, so they're both there. The dart is the particle, the wave pushes on it, and that's where it lands.
But it shouldn't always be landing at the same place.
So how would we describe, say, the double slit in this language? So we had these interfering waves in the picture that I was showing, governing the likelihood of the particle landing one location or another. In the double slit in this case, what would be the motion responsible for the interference pattern built up by the little dots on the screen?
So the particle is guided by the wave. If the motion of the particle somehow leads to an interference pattern. That must be being impressed on the particle from the wave. But the wave does indeed go through both slits. It does indeed develop an interference pattern. And in precisely the distance from the two slits, that the wave, two pieces of wave, one through the upper slit, one through the lower slit, when they start to overlap and interfere and develop an interference pattern, you see that there. You see the motion starts to get interferency with the trajectories tending to go avoiding certain regions and clustering in other regions because they're guided by a wave which has a similar structure.
Right, and just to show the equations, you mentioned there's a secondary equation, which is how, in essence, the wave pushes on the particle. You said any student could guess it.
Yeah.
Does anybody want to guess what the other equation is? If just in case. So there it is, right? So anybody could have guessed it, absolutely. But it's actually true. When you study the details of this, this is the natural equation that pops out.
You even guessed it.
I don't know if I guessed it, but I looked it up.
No, you had your own derivation of it in your.
Oh, that's true. I did have my own derivation. You're absolutely right. So thank you for you read the whole thing, even footnotes and everything. That's great. All right. So this is this approach, and you know, the nice thing about this is now particles always have definite location. They have trajectories in the traditional sense, which is a very nice feature of this. Now, other folks, what do you think about this? Sean?
Well, David Wallace, philosopher of physics, put it in the way that I find very compelling. He says, you know, faced with the measurement problem that we're looking at here, the philosophers instantly want to add new physics. The physicists are like, we just need better philosophy, right? And so as a physicist, like there's a whole nother equation, a whole nother thing. And as we'll get to, I believe in a much sparser, leaner, and meaner version of quantum mechanics. So I just think that none of this is necessary. And when you get to things beyond a single particle or a single dart, when you get to the wave function of the universe and quantum fields, it becomes much harder for this formulation to even be written down.
Ruediger, you have thoughts on this approach?
Well, I mean, this was, I very much agree with what Sean said. In addition, I would say that I would like to come back to spooky action at a distance, because Bohmian mechanics actually has explicitly discussed spooky action at a distance. If I do something here, the guiding wave changes instantaneously. It's serious if I have an entangled pair. Now, the curious thing is that there is no way physically to actually detect that change over there. Or that's the other way around. If somebody does something at serious, then the Bohmian real set of affairs, the guiding wave at this place here changes, but there is no physical way of actually finding out what that change is or finding out what the other person did over there. So for me, this is a very strong argument, a very strong sign that the physics tells me that this picture is wrong.
David?
Unnecessary.
I'm much more sympathetic to the Bohmian picture than either of the previous two commenters were. But of course, it's going to be what we think of any of these pictures is going to end up depending on what we have on the table in front of us. I mean, of the four pictures we're going to discuss today, there's maybe a useful distinction to be made. Three of them are, in a very old-fashioned sense, attempts at an objective, univocal, realistic picture of what's going on in the world. That is the Bohmian picture, the collapse picture, which I'm going to talk about a little bit, and the many worlds picture that Sean talks about, are all pictures in this tradition. The Qbist picture is something different. The Qbist picture is a way of renouncing this traditional objective,
which we will come
realist
to.
project.
Yep.
So it depends on what else you have on the table. If Sean's picture worked out at the end of the day, that is, if there were a way to make sense of our experience in the context of this Everettian interpretation, I think everything Sean says on its behalf would be crucial and important. I have worries that at the end of the day, it's not going to be possible to make sense of our experience in the context like that. Given that, I think there are very good reasons for pursuing the kind of Bohmian project that Shelley described.
So if I was to ask you in the spirit of, say, you know, America's Got Talent, right? asked to vote. You know, and voting here is not saying that you think it's the right answer, but it's sufficiently promising that it's worthy of further development on this approach that Shelley was describing. How would you vote? So if we can actually bring up our little scoreboard here. So on this de Broglie-Bohm approach, David, what say you?
Yes.
Yeah, so here we go. Oh, and yeah, okay, good. All right. So, Sheldon, I suspect...
No, I don't like it.
I'm going to vote for you. Yes, there we go. Okay, good. Sean?
I think I was thumbs down.
Yeah, you think you were...
remember the past.
Well, actually, we thought, we were trying to predict what you'd say. You'd be like, you know...
I said it was the second best.
Maybe it would work. All right, so a thumbs down to a maybe.
Yeah,
Ruediger.
that's a good one.
Thumbs up, thumbs down, something in between. And you gotta say thumbs down, because that's what's gonna come up here. But you know, you can go otherwise too. Now it's a probabilistic scoreboard, and there's a high probability that it's gonna come out thumbs down.
You see, the only thing I object with is saying, well, not worth of further development. That is a very sort of, I mean, it's sort of an unscientific thing to say. So.
See, the physicists are just as bad as the philosophers.
Okay, so, no, your qualification is absolutely important, and people around the world have heard it. This is just sort of a very coarse description of your perspective. All right, so there's our first approach. And now what I want to do is immediately move on to
How
the
come
second.
you don't vote?
Why don't I vote? I'm meant to be the objective moderator here, but maybe I'll jump in here or there at some point. So, the many worlds approach to quantum mechanics, a completely different solution to this measurement issue that brings up a whole lot of other fantastically interesting ideas. Give us your best shot convincing us that this is the way to think about it.
Yeah, you'll all be convinced.
There we go.
At the end. You gave this wonderful quantum algorithm that we're all taught in physics undergraduate school. You start with a state of the universe, a wave function, a quantum state. It evolves with time. There's some equation, Schrodinger's equation. And then if you were to make a measurement, the probability of getting a measurement outcome is proportional to the square of the amplitude that obeys that equation. Okay, so clearly it's step 3 that is the embarrassment here, right? It sounds different than anything we've ever heard. It's awkward and whatever. So many worlds is the following. You have a state, a quantum state of the universe, a wave function. It obeys an equation, the same equation that we had before, Schrodinger's equation. Now stop talking. Just shush. That's it. That's what the many worlds says. That's the entirety of what we call the Everett formulation of quantum mechanics after Hugh Everett, who invented it. There he is, Hugh Everett. And it says, you know, that the third step, the step where the probability comes in, that happens whether you put it in or not. That naturally emerges from the wave function and its evolution. And why does that happen? Well, you remember you had the nice picture of looking for the particle in Manhattan, and you said the measuring device is going to measure, and if you just took naively seriously the equation, the measuring device itself is in a superposition. So there's one part of the wave function of the universe that says the particle was here and the measuring device found it there. There's another part of the wave function that says the particle is somewhere else and the measuring device saw it somewhere else. And the Everett formulation says, yes, believe the equation, accept the equation, trust what that equation is telling you. And you want to match, as David rightly emphasizes, you want to make sure that that sort of, you know, giving into the equation and letting it wash over you actually matches our experience, and those of us who are Everettians think that it does.
So for a picture of that, if we go back to our little dart thing, and again, criticize the image if it's not capturing the idea, you know, roughly speaking, but we might imagine that the dart now is going towards the dart board, and what happens is, in some sense, it lands in all of these different locations, in all of these different realms, these different universes, if you will, and in this approach, there's no collapsing to one outcome. All of the possibilities actually occur. So we just take a look at this guy again, just to have it in mind, to compare with the others. You got the wave, and the wave is the wave, like you said, and that's why the wave is still waving over there, because nothing's happened. The wave is still describing what's going on.
That's right. And what's crucial to this picture, especially to people who, you know, don't hang out on the wrong street corners where we discuss quantum mechanics, is that the worlds, we have many worlds here. Well, we have 9 here.
Yep.
They're not put in by hand. They were always there as possibilities in the wave function. All that Everett says is, take them seriously. They're not added to the theory. There's nothing added to the theory. There's just a wave function and an evolution equation. And we live on one of these, and it's very much as if, the world were a stack of papers, a sheaf of papers, and all the papers start out the same, and as time goes on, they become a little bit different, and every one of those is a separate world. And people don't like it, but it was always there in quantum mechanics.
So how was this received when it was first put forward? So you mentioned
Everyone
Everett.
immediately said that must be right.
What's that?
The story that I was told was that Hugh Everett was a graduate student at Princeton working with John Wheeler, and he came up with this idea, and Wheeler was a visionary physicist and old school quantum mechanics guy, friends with Niels Bohr, so he actually sent his grad student, Everett, to visit Niels Bohr in Copenhagen to say, look, I figured out quantum mechanics. And he came back so depressed that he left physics because the reception that he got was not encouraging. And I think that traditionally it's not been encouraging. It's been very difficult for people to jump on the Everettian bandwagon, but I think we have momentum. And I think especially it's because we understand the dynamics of quantum mechanics better and better. We've developed tools like decoherence and things like that. We have seen in experiments the kind of behavior that is predicted by this idea that the wave function is always there. So I think that it's just much easier now to believe in the many worlds picture than it was 50, 60 years ago.
So can I just ask you one question that comes in, and it's a natural question, I'm sure people here, but this is from Elizabeth S. in Tennessee. How can there be many worlds we can't see? How is that different from thinking about God or angels?
We have an equation. If we had an equation for God and angels, I might believe in them. Again, it is again a very good question. You're right, because what right do we have to accept the existence of all these things that we all admit we will never see? And the answer really is, that is what the equation predicts. And by accepting that equation, I find a set of predictions that match, I would claim, perfectly onto every experiment we've ever done here in the world. I think it to be our job as scientists to develop the simplest, most powerful, most comprehensive theory of the world that fits the data. And that's what many worlds is. And the worlds are there. You don't count the ontological extravagance of a theory by counting the number of worlds in it. You count it by the number of equations in it, and I have the fewest equations of anyone up here.
David, what do you think?
The worry, this is Everett's original proposal was one of the most sort of radical and heroic and thrilling and seductive, I think, proposals in the history of science. There are all kinds of reasons to get very excited about it, and I don't know anyone who I think of as smart who hasn't gone through, who knows about this stuff, who hasn't spent a good amount of time very excited about this interpretation. The question at the end of the day, this is something that Sean alluded to. The place around which most of the worries about the Everett interpretation have coalesced over the years is whether it can make sense of the chanciness of our experience of the world. This chanciness is absolutely crucial to the way we verify quantum mechanics. Quantum mechanics makes certain predictions about the probabilities of the outcomes of experiments. We do many such experiments like you were showing in the introduction. We gather up frequency information for how these experiments come out, and it's on the basis of these sorts of collections of experiments that we take ourselves to have good reason to believe in quantum mechanics in the first place. Like I say, the point around which most of the worries have coalesced over the years is whether something like the Everett interpretation can make sense of those probabilities. And the very simple way of saying where the worries come from is just to point out that this picture of the world is completely deterministic. Given the way things start out, given the initial wave function of the world, it's possible to predict by solving the equations exactly what the world is going to look like at all future times. There will be this branching structure. I will, in some sense, have many different descendants, but it's
that are all you.
That are all me.
Yeah, right.
But it's not clear how it's going to make sense to assign probabilities to my ending up as this one or that one. The worry is that it would be like saying to an amoeba that's about to split, do you think you're going to end up as the one on, what do you think the chances are that you're going to end up on the right or as the one on the left? It seems like the right answer for the amoeba to give is, gee, that's a stupid question. Probabilities aren't involved here at all. I'm for sure going to have one descendant that's on the right. I'm for sure going to have one descendant that's on the left. That seems like, at least very naively, there's a long history of discussions of this. Sean has contributed to it lately in a really interesting way. But there's been this worry from the beginning that probability talk just isn't going to make sense. If it doesn't make sense, this is not a theory that can account for our empirical experience.
So basically you're saying if I'm the experimenter in the lab, right, and there's a 50% chance I find the electron here, 50% chance that I find it there, I do the measurement. In this approach, I am going to see the electron over there, and another one of me is going to see the electron over there. So if I ask myself, what's the probability, say, that I'm going to see it over there? It's not 50%, it's 100%, because there will be a me who sees it over there.
Right.
And if I ask myself, what's the probability I see it on the left? 100%, not 50%, because there will be a version of me that sees it. What say you to that, Sean?
Well, I think it's exactly the right thing to focus in on in the Everett interpretation, unsurprisingly, since David knows what he's talking about. I always worry when David says I've made an interesting contribution, but thank you for that. What I would say is that quantum mechanics, the many worlds picture of quantum mechanics, challenges us because the way probability works in this theory is different than the way it has ever worked. And roughly speaking, we talk about objective probabilities and subjective probabilities. And objective probabilities just, there is something irreducibly random and chancy. And David will, in the dynamical collapse theories, defend that point of view. Subjective theories are, there's something, subjective probabilities, there's something that's going to happen, but we don't know because we lack some information. And Sheldon and Ruediger will defend views like that. And the Everett formulation says, well, actually, it's kind of neither one of those, which shouldn't be surprising because quantum mechanics often says that that's the answer. Everett says we know exactly the entire state of the universe, 100% accurately in principle. There's nothing probabilistic about it. It evolves deterministically. But there are circumstances like the dart hitting the dartboard. Imagine that I didn't see the dart hit the dartboard.
Yes.
Okay? So now there's a branch where the dart hit there, dart hit there, dart hit there, and there's many copies of me. I know everything there is to know about the universe, but I don't know which copy I am. So that's a kind of subjective probability that arises naturally from the objective deterministic evolution of the world.
All of your copies can say the same thing.
They will, and we'll argue that there is one unique, sensible way for them to behave, and it turns out to precisely fit the data.
You mean if they were betting on the outcomes, what would be the smart bet to make, and somehow it all works out, that if they bet according to the probabilities as usually calculated, they'll maximize the return, something like that.
That's one way of doing it. I mean, like many right answers, there are many different ways to derive it, but yes, we get the right answer.
Gotcha. Ruediger, thoughts on many worlds?
Well,
you've converted, you just realized.
In which universe?
My worry is that in a theory in which everything happens, we are actually not saying anything about the world we are in. That's really it.
Thank you. Shelley, thoughts on many worlds?
I was once sympathetic to it. It does have the virtue of having one equation. Bohm has two equations. Standard textbook quantum mechanics has maybe an infinite number of equations because it's never really fully written down.
Yeah.
So having just one equation is very nice. My problem with it, I have two problems basically with, maybe more than two. One is, it's not so much that I don't see how probabilities can arise in the theory in a way that we would see random results in some sense, but rather that I just don't have the sense that the probabilities really come out convincingly. Not at all convincing. I would have expected different probabilities according to that theory than the usual ones. But that isn't so much my main difficulty. My main difficulty is I have the sense that it's based on a mistake. A mistake everybody took, almost all physicists just somehow took for granted. That is taking the wave function as the only element of the reality. The only thing that's real for a quantum system is its wave function. As soon as you say you've got more than wave function, well, then there's no need whatsoever for many worlds. And what I find striking is that This dogma that the wave function is everything even extends to so many physicists who don't regard the wave function as real at all. Many physicists, it's far less than a majority of physicists that take the wave function seriously as something objective, real. When they say, many physicists, when they say it's a probability wave, they really mean it just reflects our information, it's subjective, not something really out there. Nonetheless, many of those same physicists will still say, but there's nothing more than wave, which would seem to suggest there's nothing.
The simplest solution of all.
So that's going to be a problematical theory.
All right, so if we can go back to our little chart, our little scoreboard, just to get a sense here. So David, on many worlds, is it worthy of further pursuit? You think it could ultimately be?
Yeah, I'm sympathetic to this claim that one doesn't want to ever say about anything that one shouldn't study it further.
Telling you.
But I'm willing to accept a thumbs down.
Thank you. Shelley.
Thumbs down might be a little bit too strong, but I'm close
I think you're a pretty strong guy, So that's good. Yeah,
that's good.
Well done in the booth. Thank you. Quick
Fixing it. Yes.
Sean, I assume that
2 thumbs up.
2 thumbs up. I don't know if we can do that, but we'll definitely come back to it. Ruediger, you seem
I think there's hardly a doubt about what that will come out.
Ka-chunk, there it is. All right. So, two proposals. Let's move on to the third one. And David, that's one that you're going to describe to us, which is spontaneous collapse.
So this approach is more or less, especially given the way the problem is usually set up and given the way you set the problem up. Here, this is the sort of most pedestrian, straightforward, obvious first thing to think of, and that is, look, you solve the equations of motion as they're given to us. They give us this weird result where there's a superposition of seeing this and seeing that. As you said, our experience doesn't, at least insofar as we understand it, look anything like that when we do these experiments. So the obvious thing to do is to think about modifying these equations. The rough idea of doing something like that, because it's so obvious, goes very far back. I mean, you find this in Schrodinger in the 30s. You find it in von Neumann's famous book, Mathematical Foundations of Quantum Mechanics. But the way von Neumann formulated it, for example, was to say, okay, apparently there are 2 laws rather than 1 about how the wave function evolves, and they apply in different circumstances. When the system of interest isn't being measured, it evolves according to the Schrodinger equation, which you put up before. When the system is being measured, it evolves instead according to this postulate which dictates that the wave function collapses into this sharp peak around whatever result is obtained. Good. As it stands, this just doesn't count as a serious candidate for a fundamental theory of the workings of nature. It involves this English word measurement. It depends on whether or not a measurement is going on. And at least the ordinary English meaning of that word doesn't have remotely the requisite precision to play this kind of role in a fundamental picture of nature. So a problem arose about, a question arose about how to precisely delineate the boundary between those circumstances in which the Schrodinger equation governed the evolution of the wave function of the world and those circumstances in which a collapse postulate governed the evolution of the wave function of the world. And the history of discussions of trying to locate this boundary for something like 50 years, I think it has to be said, is a kind of, wince-inducing very undistinguished discussion in the history of physics. So you have people invoking all kinds of other vague words that are clearly no better than measurement. You have people invoking distinctions between the micro and the macro in order to locate this boundary, or between reversible processes and irreversible processes in order to locate this boundary, or between animate systems and inanimate systems in order to locate this boundary, or between subject and object in order to locate this boundary. It presumably should have been clear to everybody from the word go that none of these other distinctions was going to be any sharper, was going to be any more useful than the original distinction that von Neumann was talking about between circumstances in which measurement is going on and circumstances in which measurement isn't going on. And like I say, the discussion went around in sort of pathetic circles like this for about half a century or more, until the early 1980s, when finally three Italian physicists, Ghirardi, Ramini, and Weber, actually wrote down a fully explicit, mathematically precise theory of collapse. The theory didn't end up working in exactly the way all these previous discussants, that is, Wigner and von Neumann and Bohr and those people, had anticipated. That is, it didn't do something like locate a sharp boundary between those circumstances in which collapse occurs and it doesn't. Rather, they modified the Schrodinger equation in a way that applies to every single physical system at all times. But they came up with an extremely clever way to modify it that had the consequence that for all situations except the situations that are characteristic of measurement, or a little bit more generally, for all situations except situations where you're dealing with a macroscopic object that's in a superposition of two different spatial locations. For all situations other than those, their modified equation gave almost identical results to the standard Schrodinger equation. But they came up with a way of modifying it such that in those troublesome situations, it departed dramatically from the predictions of the Schrodinger equation and actually gave you something like a collapse of the wave function, as you were talking about, onto one of these peaks or another. So like I say, the basic idea here was around from the beginning. This is the most flat-footed and obvious way to respond to the measurement problem as it's usually presented. It took a long, long time for somebody to make these ideas precise, and we now do have this very simple, straightforward, elegant mechanism due to Ghirardi, Ramini, and
So as I understand it, basically, so when it comes to individual particles like a single electron,
right,
they behave more or less very close to the way they would have in the standard approach.
Very, very close.
But the idea is if you've got many particles, many electrons and quarks and neutrons, a big collection of particles, there's a new physical phenomenon that kind of hits one of those particles, causes its probability wave to spike or collapse, and then downfall the dominoes. The whole thing then materializes in a definite way.
That's exactly right. That's exactly right.
He taught me this. That's why I know I get it right. So just to give you a sense, we have a little visual of this. So again, back to our dart, and the idea is we'll hit this guy with that collapse new equation, that new phenomenon, just dictated sort of by that little flashing light there, and then sort of, as you're saying, downfall the dominoes and the whole thing materializes, and that's the new way of thinking about it in this GRW or spontaneous collapse approach. I think we have this guy a second time just to run this guy through again. So again, it's a probability wave function. You have this new phenomenon from GRWs, collapses on a particle, and that causes all of the other ones to collapse as well, giving us this definite outcome. So we basically are taking the old idea and making it happen with a new...
And making it explicit, making it precise, reformulating this old idea so that it doesn't depend on words like measurement or macroscopic. Rather, of course, it's a consequence of this theory that macroscopic objects don't remain in superpositions, that measurements have determinate outcomes, but that's not because words like measurement or macroscopic are playing any role in the fundamental formulation of the theory. Rather, that's something we can prove about these things from an exact fundamental formulation of the theory, such as Girardi, Ramini, and Weber gave us.
Right down. Ruediger, thoughts on this approach?
Well, let's just say something about all three, which they have in common, because David earlier said that Qbism stands out. So they all three have in common the following view of the world, of reality. There is, let's say, you know the state of the world right now. That determines, essentially for all the future, what the probabilities for future events, for anything that happens in the future will be. So this is actually very similar to a 19th century view, to a 19th century deterministic view, where, or let's say Laplace's view, where if you knew the state of the world now, you could predict exactly what happens at any stage in the future. With the one difference, which is important, of course, but really not that radical, that what we predict in these three theories is not the precise things that happen, but just the probabilities. So in that sense, I mean, this is just one particular view of the world. And so what Qbism does is in
which
contrast,
we will again finally come to in about 3 minutes. We've heard this word all night.
Is
we're
just explore a different route, a different view of the world. And so this is really one reason for not wanting to pursue GRW.
Sean, quick thoughts on spontaneous collapse?
Yeah, I think
resonate with you at all? Or?
It's one of those things that certainly could be true, but if it turned out to be true, I would probably retire as a physicist. And this is something where, you know, any of these could be
Why,
true.
it's just too ugly, or what?
Well, it seems to just come along with all sorts of weird and unnecessary things. For one thing, the past and the future are radically different in a theory like this, right? Than they had, and one of the great triumphs of physics from Newton through superstring theory is that the past and future are on an equal footing. It's an intrinsically probabilistic law, which I think that we can get away from. It's sort of a recipe that works in the situation of darts or electrons, doesn't work in any obvious way for the real world, which is made of quantum fields or quantum space-time or something like that. And maybe someone could find something like that. But it seems to be repudiating, therefore, so much of the success of the last 100 years of physics for what I don't, you know, is pushing on an open door. I don't think that we need all that extra stuff to solve the problems.
Shelley?
One thing that perhaps should be said, I don't know if it was said, that unlike the other approaches mentioned here, and this is not so much a criticism, not really a criticism, but this GRW, spontaneous localization, is in fact, it's different in the sense that it makes different predictions from quantum mechanics.
Right.
Well, all the other possibilities
That's a key point.
make exactly the same predictions, presumably. If they work, anyway, they're claimed to make the same prediction. This makes different predictions. So in that sense, it's fundamentally...
So it's a different theory, and in principle, you could...
Well, I would say all of the things are probably different theories, but three of them are empirically
You can make you can design experiments in principle.
Yes.
These experiments are difficult to do with currently available technology, but in principle, we know how to design experiments for which GRW or any of the similar family of theories of spontaneous collapses will give different predictions than either Bohm or Everett or Qbism.
Let me mention what I think is two problems with it. One is the modification of Schrodinger's equation is pretty ad hoc. Second,
and you notice I didn't write that one down because that one is, you know, basically what Sean is saying. It's too much of a pain to write it down. Too many features to actually even give a
too
sense
much
of what
arbitrariness in it.
Yes, I agree.
Second, one of the most beautiful equations in quantum mechanics is Schrodinger's equation. You lose that nice equation.
Yep. All right, so...
I should say,
go ahead.
I should say very quickly, by the way, that the three theories we have here that attempt to make the same predictions, or purportedly make the same predictions, do so because they're cooked up to fit the data, the experiments we've already done. As a cosmologist who spends time thinking about the whole universe, much of which doesn't have any observers in it, I think that our theories are different in those regimes when you don't have measurements going on. I think that's very, very important for modern cosmology.
Yep, yeah, absolutely. All right, so back to our quick chart, if we can just get a sense here. David, what do you say about this approach?
I think it's worth pursuing.
You think it's worth pursuing?
Yes.
Yes, okay, we guessed it right. Shelley?
Yeah, I think it's worth pursuing.
Yep, all righty. Sean? Oh, well,
Everything, but no.
unless you want to retire.
Yeah, I know. It's worth other people pursuing.
I give you a, I think it's reasonable.
Well, it's a testable theory, so worth pursuing.
Good, all right. So we are now to our final candidate, Qbism. So we've heard this word a few times mentioned. Ruediger, tell us what this approach is about.
Okay, I bought a quantum system to do an experiment on. So let's just flip this quantum system. Okay, so what's the probability of heads?
100%, many worlds approach.
Okay.
I'm sorry, let me play along, 50%.
Well,
Is that what you want me to say? You played along with me, so I'll play along with you.
Stick with 100%.
Oh, so,
I have 0% for heads. Okay. My point being, the probability, you have a different one from me, so this is actually about you and about me. It's not about the system directly. So the probability actually is your belief or my belief about what you will see if I show it to you. I can show it to you. You see, it's tails.
He was right, yeah.
So
take us a little further, so I fully understand what this is about.
So probability in this is, I mean, just an example for how probability is used in Bayesian personalist probability theory, which actually is a modern full account of probability, which is used widely in statistics, economics, and some parts of physics. So this is a respected and very useful, and actually, I believe, the only really fully consistent approach to probability. Probability is belief about what you will experience, what you will see. Now, what Qbism says is that you do not need to modify the concept of probability for quantum mechanics. So even quantum mechanics, probabilities are personal degrees of belief. So basically, the probability I write down for a measurement outcome is my expectation of what I will experience when I perform the experiment. So the point is, the probability is not a property of this coin. This is on my hand. The probability is actually my belief. And now quantum states are equivalent to probabilities. Quantum states determine probabilities of outcomes. Quantum states are fully mathematically equivalent to probability distributions. So in that sense, probabilities are an experimenter's or an agent's expectations, or quantum states, sorry, I said probabilities or quantum states. Quantum states encode an experimenter's or agent's expectations for experimental outcomes. Now, what that says about the measurement problem is that it just dissolves. Because probability theory has no measurement problem, has no collapse problem. When I write on a probability for some experiment, I observe the outcome, but nothing collapses. The probability just becomes useless, because, I mean, has done its job, and you don't need it any longer. Or if you have a situation where you actually just get partial data and want to update probabilities for the future, all you do is you update your own expectations for the future, but nothing in the world collapses.
And you update them by the observations themselves.
Exactly. I experience an outcome, I update my own expectations for the future.
So can we give a little visual, mental mnemonic for this one? So this fourth approach is the dart is going, and the idea is, if we're not looking, if we're not actually yet doing the observation, there's nothing really we can say until the observer looks. And so there, if we bring our observer, Ruediger takes a look, and then you look and you take in the observation, you update your understanding of the world based on your observation. Is that sort of roughly capturing what you were saying?
Well, I told
you got a guy in Times Square to do that. I thought he did a pretty good likeness. Not bad, right?
Yes,
those guys, out there, like,
from that,
like $10, you can do it. Anyway, go ahead.
Well, you see, when we do science, what are we doing? We're making predictions, and we test these predictions in experiments. So this is really what Qbism talks about. quantum mechanics is, I mean, this must be the reason why most physicists are not interested in the interpretations of quantum mechanics. It is because quantum mechanics is a tool they can use to make predictions, to design experiments, to build machines, to build, quantum mechanics has transformed the world in a way that has, that is unprecedented. Now, in all these experiments, experimental designs, predictions, including cosmological predictions, you never actually need to talk about Bohmian hidden variables, about spontaneous collapse, not even about the wave function of the universe. You just apply quantum mechanics as a tool to make predictions, to verify these predictions. And that works. And this must be the reason why most physicists are not interested in the interpretation of quantum mechanics.
So what do you say to people that would be have some discomfort about this? Imagine what the universe was like before there were observers, right? So no one was having any of these experiences. Does your approach somehow give a description of the world that would make me comfortable about it happening out there, even if there's nobody looking at it? Is that something that I should worry about?
Well, I would hope so, because when you do cosmology, what do you base your cosmology on? You base it on what you observe or experience now. I mean, this is really all you can base your theory or your thinking or your cosmology on. What are the cosmological predictions or your conclusions you draw? Well, they are, if they're good cosmology, they're about your future experiences. They're about your future predictions. I mean, you will never stop at just saying, well, I have explained how the things are now, because there may be many ways of doing it. You test your cosmology by making predictions, and then, for instance, about the particular fluctuations in the background radiation, and you test them. So even cosmology is about taking your present and, let's say, your past experiences and using the theory, using quantum mechanics as we know it, to make predictions about future experiences. So it fits perfectly well into that framework.
Now, I'll give everybody a shot in a minute to give your thoughts on this. One thing that you mentioned early on was spooky action at a distance. And let's just come to that now, because it's interesting to see what Qbism says about this. So the traditional way of thinking about it, if we could bring up our system. So imagine we have these two arrows. It's called spin a half in quantum physics. But imagine that we have these two entangled particles whose spins are up and down, but in a correlated manner. Now, the traditional spooky action at a distance arises if I go and I measure, say, the particle on the left, right? And through my measurement, I cause it to take a definite reality, say, spinning up. Then, according to the mathematics, the distant particle also snaps out of this fuzzy haze of possibilities and spins down. And that's weird, because I did my measurement over here, but I seem to have an impact over there. This is what Einstein called spooky. Now, in your approach, the spookiness evaporates, if I understand it. Can you describe to us where it goes?
Well, I should have worn different color socks here, because in the Qbist approach, these correlations, this situation is very much like Bertelsmann's socks. Bertelsmann was a colleague of Bell, I think, at the University of Vienna. I'm not exactly sure about that. And he used to wear different color socks. And so when Bell saw him coming around the corner, when he saw one foot, one sock, he knew immediately what the color of the other sock would be, namely different. So, so nobody would call it spooky action at a distance. So what Qbism says here is that if I have a belief about these two, because this is what the quantum state is. This is a belief about what I will see, experience when I make an experiment on this or on that particle here. What happens is if I make a measurement on this particle here, I see it, I experience spin down, I see spin down, and then I update my expectation for the other particle here. Now, of course, people...
And now to get the information of the other particle, it has to somehow travel to you, the result of that experiment.
Well, for instance, or I have to go over there and...
Or you go over there and you look at it. So there's nothing happening at a distance, because if it's all about what you observe, you are certainly always nearby your own self, and therefore there's no spooky action at a distance, because it's all about you.
It is not all about me. It's about, I mean, you mentioned...
Or each observer.
No, even not that. It is always about me and the world. Because I mean, Qbism emphatically says not that it is all about the subject, nor is it all about the world. Any measurement is an action a subject, an observer, a physicist, system takes on the world. And so measurements are active processes, they're actions, but these actions you elicit an experience, and the measurement outcome is the experience. So any measurement is an action on the world, and it needs the subject and the object, it's where the experience and the world meet.
But that experience is something that the individual, the observer has. That's the point.
Yes.
Yeah, good. So, what do you think, David?
In the beginning of quantum mechanics, there were figures like Bohr, who announced that something really earth-shaking had occurred. Not just that the world was different than we thought it was, but that the world was in a fundamental and irrevocable way less susceptible to scientific penetration, as it were, than we used to think. That the project, that the old-fashioned scientifically realist project of representing the world, you know, of giving the view from nowhere, as it were, of giving a univocal, objective, factual representation of what the world was doing, from which all of our experience could be derived, figures like Bohr announced that the really profound lesson of quantum mechanics was not this or that lesson about how atoms behaved, but a much deeper, much more earth-shaking lesson to the effect that this whole set of aspirations had somehow been exposed as quaint and naive and old-fashioned and outmoded, okay? And when people said, but shouldn't we look harder for some way of understanding an actual picture of the facts of the world from which all this would follow, what they were told again and again was that there were proofs, that there were arguments. These proofs go back to von Neumann. Bohr thought he had arguments along these lines, so on and so forth, that no such thing was available, okay? If this is the case, this is indeed a sort of unspeakably profound moment in the history of human thought. What's happened since then is that it's been discovered that these announcements of the death of this project were in all sorts of ways premature, okay? We now have perfectly old-fashioned, realistic models of the world which explain the emergence of our experience, okay? I take it, nobody on this stage has so far claimed that, say, Bohr and GRW don't do that. The complaints about it has been...
Bowman GRW?
Bowman GRW, excuse me. Bowman GRW don't do that. There's some question about whether Everett does that or not. Some people say yes, some people say no. But there doesn't seem to be any dispute that there's a possibility of doing that. The complaints about some of these realistic theories are they're too complicated, they have two equations instead of one, blah, 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 blah. This seems like fairly small potatoes compared to the existence of a comprehensible external world at all, okay? So now that we have these other examples, it just seems crazy. There's an interesting project of comparing these realistic theories to one another, of finding out which one works best, of finding out which one best satisfies our taste for elegance and simplicity, and so on and so forth. But the idea that because some of these theories have two equations rather than one, the appropriate conclusion is to give up on the existence or comprehensibility of the external world at all seems crazy to me.
So your real thoughts on?
I think
you want to respond.
I think I would like to respond. I think I have to say at least three things. The claim that the so-called realistic theories explain experience is bold.
Is what?
Bold. I don't think that any.
You mean they don't explain why the experiments come out the way they do?
The second point is that Qbism does give a comprehensive view of the entirety of my external world. It's just an agent-dependent world. So every agent can explain all aspects of his experience, all aspects of the external world, using quantum mechanics. So furthermore, there is sort of a Copernican principle. I can use quantum mechanics to describe or to make predictions about you. You can use quantum mechanics to make predictions about me. So there are really no aspects of the world which are beyond quantum mechanics in this sense. And the third point, or maybe the fourth point, is that Qbism does not give up the project of saying something about the world and saying something objective about the world. It's just Qbism says something different about the world than what your project is, namely mapping parts of your mathematical theory or mathematical objects to the reality of the world, giving this one-to-one mapping. So Qbism has a different project, and maybe one of the biggest clues that it might be on the right track is that none of these additions to quantum mechanics that you find in GRW or in Bohmian mechanics are actually necessary to use quantum mechanics, to do quantum mechanics, to explain all the experiments that have been done in the last 90 years. So even explanations and comprehensibility are not sacrificed here.
So we're 2 minutes over, so we have to wrap this up in about 1 minute. I just want to finish out our little table, and then I want to ask one final question before we wrap it up. I am going to vote on this one. The part about your approach, which I find quite compelling, is looking squarely at probability and trying to use a better understanding of it to give us a better understanding of how it applies to quantum mechanics. So whether or not the particular approach that you've come up with is the right one or not, we don't know, of course, but I'm going to give it a thumbs up as an approach that I think really is worthy of further development. David, what do you say about Qbism?
Look, once again, there's been an enormous amount of work that's come out of Qbism about understanding the mathematical relations among various probabilities that we encounter in quantum mechanics. I think this has been enormously useful. So I think there have been, my attitude toward this, I guess, is that it's a project whose core vision seems to me very confused and poorly motivated, but which has had lots of spin-offs which have been great. So I guess if the question is, do I think of it as promising as an attempt to solve the fundamental riddles of quantum mechanics? No. Do I think it's had useful and illuminating spin-offs? Yes, many.
Great. So I don't think we even need to go to the chart, because it's late. Because I don't know that we would capture the nuance. Yeah, and thumbs just don't quite cut it anymore. Yeah. Thoughts on this approach?
No, I totally agree with David. There ought to be room in physics for understanding what's in the world and how it behaves, even if there are no agents in it. Agents are very interesting, and we like to understand agents, and there are Kavli prizes for understanding agents. But that understanding of agents is often in terms of inanimate stuff, not in terms of other agents.
John?
I think it's probably true that I just don't understand Qbism or quantum solipsism as well as I should. But it seems to me that one needs in that approach some mechanism for talking about the wave function and how it evolves. And the difference is that in our approaches, we take that wave function or whatever extra bits we have, and we say that's the real world. This is some description of reality. And in Qbism, it's just a tool that, if you were to take the Everettian calculational schema and did Qbism on it, you would say, yes, there's all these other branches of the wave function that are predicted by Schrödinger's equation, and the way that we deal with them is saying, but they're not real. We don't need to talk about them. And that seems more like therapy than physics to me. And I don't, as I said before, think it's necessary.
You're in New York, though. Therapy is a big, big thing here.
And it can go on for years.
Yep. So final question as you wrap it up. Imagine we're at the World Science Festival, I don't know, 2025, 2050, I don't know, 2100, whatever. Will we have an answer? Will there be consensus on this? Or are we just going to continue with various ideas, and is that what the future will hold? David, what do you think?
Look, I think that because of some of the history I described before,
Yep.
the serious discussion of these questions isn't more than about 20 years old now. The serious, widespread
Yep.
discussion of these questions. The questions came up 100 years ago now. There was a long period of people sitting in their bathtubs having very idle and pointless discussions about this. So I think that the serious discussion of this only got started in the last 20 years. Yeah, I think there's every reason to be optimistic that 100 years from now there'll be a consensus.
Ruediger, what do you think?
Well, David Merman, who is a collaborator on this project, in an email he answered and he CC'd me on, said, well, his prediction was that 25 years from now, everybody would have accepted Qbism as the answer, and so the field of quantum foundation would have sort of faded away.
All right. Shelley?
I think more likely than there'll be consensus on this is that by the year 2100, quantum mechanics will have been completely replaced by some totally different
Wow, it's a radical answer. What do you say, Sean?
Yeah, I think 50 years from now, 97% of working physicists and philosophers will agree on one formulation of quantum mechanics.
All right, so come back to the World Science Festival 2100 to see if the predictions are borne out. Please join me in thanking tonight's panel. Great job, guys.